In the previous lecture, we have discussed in very detail the Einstein's A and B coefficients. Now, today we are going to see some of the more important facts regarding these Einstein coefficients. Actually, you know that due to the spontaneous emission of radiation, we simply get the incoherent radiation, while on the other hand, the stimulated emission, which was predicted by Einstein in 1916, we get actually the perfectly coherent radiation. So, if you want to get a highly intense beam of emitted radiation, or in other words, you can say if your aim is to find a highly amplified beam of radiation, then definitely the stimulated emission of radiation must dominate over the spontaneous emission. Only then we can get a highly amplified beam, because as I have told you that actually the spontaneous emission gives out radiation at random moments and in random directions, and so the radiations emitted by spontaneous emission is perfectly incoherent, not coherent. Okay, but the stimulated emission, on the other hand, has a very important property that if a narrow beam of radiation passes through a region containing only excited atoms, then you know the emitted stimulated radiation has the same direction as the stimulating radiation. See this figure. If you consider that this h nu is the stimulating photon, and it enters into an atomic system in which already the atoms are in excited states, then you know due to the interaction of the field of this photon, an atom from the higher energy level transits to the lower energy level, and a photon will be emitted, and that emitted photon actually moves strictly in the direction of the incident photon. So now in this region we have two photons. Okay, see here, this is first photon and this is second photon, and both have same energy, same frequency, same direction of motion, same phase, same state of polarization. Okay, now these two photons will stimulate the extra two atoms in the excited state, and so they will suffer transition from level 2 to level 1, and again we will get two fresh photons. These two fresh photons have also the same energy. You can see here. Now the stimulating photons, the number of stimulating photons is 2, and due to that stimulation we get the two stimulated photons. So as a whole, now there are 4 photons moving in the same direction, and all these 4 photons have the same energy, same frequency, same state of polarization, same phase. So in this way you can see that the number of photons is increasing in geometric progression due to the stimulated emission of radiation, and so you can say that we will get a highly amplified beam of radiation due to this stimulated emission of radiation. So in nutshell, in one word, you can simply say that if our aim is to get a highly amplified, strictly coherent beam of radiation, definitely the process of stimulated emission must dominate over the process of spontaneous emission. Okay, and now we will see how this is possible, or when it is possible, not how, but when it is possible. Now we will see it. For this, let us consider our atomic system is in thermal equilibrium with the radiation. and you have already studied in the previous lecture that what is the rate of spontaneous emission and rate of stimulated emission. Actually, if we want to find the ratio of the rate of spontaneous emission and the stimulated emission, then you can find it like this, because spontaneous emission, the rate of spontaneous emission is given by A21 times N2. If you consider two energy levels, this is 2 and this is 1, and you have considered that in second level the number of atoms per unit volume is N2, and in the first level the number of atoms per unit volume is N1. Okay, so the probability rate of the spontaneous emission is equal to what? This is A21 into N2. Here A21 is Einstein's A coefficient for the spontaneous emission, and the rate of stimulated emission, this is given by this much, B21 into N2 times U nu, where you know this U nu is the spectral energy density of radiation. Okay, and so here N2 and N2 will cancel out, and this ratio will be simply A21 over B21 times U of nu. Okay, and as we have obtained the expression for U of nu in the previous lecture, and from that you can see the value of A21 divided by B21 times U nu will be simply equal to e to the power h nu by kT minus 1. Okay, minus 1. So now from this result we can get the following two conclusions. If you consider that if h nu over kT, sorry, not h nu over kT, but simply say h nu. If you consider that this h nu is much greater than kT, then actually this e to the power h nu over kT will be much greater than 1, and it will be a very large number. This will be a very large number, because you know e to the power x is equal to 1 plus x square by factorial 2 and so on. Since x is very large, h nu by kT is very large, then this will be a very large number, and so you can say that this R will be much greater than 1. This ratio R will be much greater than 1, and this implies if R is much greater than 1, what will happen? It means A21N2, this is much greater than B21N2 into U of nu. So in this condition, actually the spontaneous emission will dominate over the stimulated emission. So in this condition, the spontaneous emission will dominate over the stimulated emission. emission. And so it is not the favorable condition for getting the laser light. So it is not favorable to get highly amplified beam. So when h nu will be much greater than kT, then that will be not favorable for getting the highly amplified beam. For example, let us consider we considered particular numerical values to clarify this concept. Let us take, if you consider that this T is equal to an ordinary temperature, this is in fact 10 to the power 3 Kelvin, okay, and we consider nu equal to frequency of light, this is 5 into 10 to the power 14 second inverse, or you can say hertz. This is actually the frequency of visible light. Okay, if you consider, then let us see what will be the value of h nu by kT. H nu over kT. You know, h is Planck's constant, and this is 6.63 10 to the power minus 34 joule second. Okay, and nu you have considered 5 into 10 to the power 14 second inverse. Okay, and divided by K is Boltzmann constant, and its value is 1.38 into 10 to the power minus 23 joule Kelvin inverse. Okay, and temperature T we have considered ordinary temperature, that is 10 to the power 3 Kelvin. Actually, when you will simplify this, you will get it is equal to 24. And therefore, if we will substitute this value in equation 1, what will be the ratio R? Therefore, R, which is equal to in fact A21 by B21 times U nu, that will be equal to, that is equal to e to the power h nu by kT minus 1. Okay, so this will be e to the power 24 minus 1. 24 minus 1. Okay, in fact this will be almost equal to 10 to the power 10. 10 to the power 10. So what you are seeing here. So therefore you can say that this A21 you can also multiply by N2. So you can see A21 into N2, this is much greater than B21 N2 times U of nu. And this result implies that the spontaneous emission is dominating over the stimulated emission. So a spontaneous emission is much greater than stimulated emission. And so this is not the favorable condition for emission of the highly amplified beam or you can also say that this is not the favorable condition for the production of laser. Okay. Now, if just in a reverse manner, if you consider that if h nu is in fact much less than kT, h nu is much less than kT, just we can have considered here the reverse condition, then e to the power h nu by kT minus 1, this will be much smaller than 1, and therefore you can see this ratio R, which is equal to A21N2 over B21N2 times U of nu. This will be much smaller than 1. And if it is much smaller than 1, what does it mean? It means B21N2 times U of nu, this is much greater than A21 into N2. This is much greater. And if it is much greater, this implies that the stimulated emission dominates over the spontaneous emission. Now let us take a proper example for this condition. We take a proper example. Let us take nu equal to 3 into 10 to the power 9 second inverse. Actually, this is just the frequency of a microwave. Okay? And we consider the temperature is simple, the normal room temperature. Let us say this is 300 Kelvin. Okay? In fact, in this condition, when you will calculate the value of h nu by kT, this h is again you can see 6.63 10 to the power minus 34 joule second. Frequency is 3 into 10 to the power 9 second inverse divided by 1.38 10 to the power minus 23 joule Kelvin inverse, and temperature is 300 Kelvin. When you will simplify this, you will get this is 5 into 10 to the power minus 4. So you can say that this is much smaller than 1. And therefore, what will be actually the value of that ratio R, which is actually the ratio of the spontaneous emission, that is A21 into N2 divided by B21 N2 into U of nu. This is equal to what? This is, you know, this will be equal to e to the power h nu by kT minus 1, and this will be equal to what? e to the power h nu by kt, you have obtained that this is equal to 5 into 10 to the power minus 4, and this is minus 1. This is almost equal to 5 into 10 to the power minus 4. But how? Because you know that when e to the power x, this is 1 plus x, if x is much smaller than 1. So here at the place of x there is 5 into 10 to the power minus 4, which is much smaller than 1. So when you will actually expand it, this will be 1 plus 5 into 10 to the power minus 4 minus 1. So this 1 and 1 will cancel out, and this is 5 into 10 to the power minus 4. Okay? In fact, all the terms containing the higher power of x will be neglected here because x is much smaller than 1. So in this condition, you can say that this ratio is much smaller than 1. So this result implies that this a to 1 into n2, this is much smaller than b to 1 n2 into u of nu. So what actually this result gives information? You can see this result shows that in this condition the stimulated emission is dominating very much on the spontaneous emission. So this implies stimulated emission is dominating on the over the spontaneous emission. Okay. So in this condition we will get actually the highly amplified beam. So if your aim is to get highly amplified beam, you can use the exciting radiation of the microwave region. And actually on this basis, first of all, MASERS was constructed. Okay. So you can say that this means that the stimulated emission rate is much higher than the spontaneous emission rate, and hence amplification in this region is possible and has been obtained in case of MASERS. Okay. So I think you have clearly understand that how we can obtain the highly amplified beam of radiation, and for that definitely the stimulated emission should dominate over the spontaneous emission, and for that the wavelength range of exciting radiation must be of microwave range. Actually the use of the optical radiation, that is you can say the visible light, you can't get highly amplified beam of radiation, because in that condition a spontaneous emission actually dominates over the stimulated emission. Okay. Now we will see a very simple but very important concept of the spontaneous lifetime associated with a two-level atomic system. So what is a spontaneous lifetime? A spontaneous lifetime. Particularly we are talking about the spontaneous lifetime associated with the transition from energy level 2 to energy level 1. A spontaneous, mark this, a spontaneous lifetime for the transition for the transition 2 to 1. What is this spontaneous lifetime for the transition 2 to 1? We will see. Actually, let us consider an atom in this level 2, this energy level 2. And this atom make an spontaneous transition and transit to the energy level 1. Okay? And we consider that only this transition is possible. That is 2 to 1 is only possible. So definitely the number of atoms in this energy level 2 will decrease, and on the other hand the number of atoms in energy level 1 will increase. So the number of atoms in energy level 2 gets depleted and it decreases. In fact, if you consider that N2 is equal to the number of atoms per unit volume of level 2 at T equal to T. Okay? Then the rate with which this N2 is decreasing, because atoms are transferring from energy level 2 to 1, so N2 will decrease with time. Then the rate of decrease of N2 with time will be equal to what? Since it is here N2 is decreasing with T, so this derivative will be negative, and that will be equal to simply minus A21 times N2. Okay? This will be equal to minus A21 times N2. Now, from this result, we can easily find what will be the value of this N2 at any time T present in this second energy level. So let us arrange that term here. You can see dN2 by N2 will be what? This is equal to minus A21 dt. And to get the value of N2, let us integrate it. So dN2 by N2, this is equal to minus A21 integral of dt. Let us take this transition starts at T equal to 0, and we are considering the process at any time T. And if at T equal to 0, we consider that the number of atoms per unit volume in energy level 2 is N2 of 0, and at time T it is N2 of T. Let us consider. Then you can solve this equation very easily. The integral of dN2 by N2, you know, this will be simply log n. So this is ln of N2, and limits are N2 of T and N2 of 0. Okay? And this is equal to minus A21 times T. Now substituting the limits, you can see this will be log N2 at T minus log N2 at 0. And this is equal to minus A21 times T. And log A minus log B, you know, this is equal to log A by B. So this will be log N2 at T divided by N2 at T equal to 0, and this is equal to minus A21 into T. And so N2 at T over N2 at T equal to 0 this will be equal to exponential e to the power minus a21 into t, and therefore at any time t the number of atoms present per unit volume of energy level 2 will be equal to what? This is n20 times e to the power minus a21 into t. Let us say this is equation A. Okay. So you can see that the number of atoms in energy level 2 is decreasing exponentially with time. If you will plot a graph of n2 of t in against of this time t, you can see when t is equal to 0, then n2t will be equal to what? This is n20, because t is 0, e to the power 0 will be 1. So at t equal to 0, the number of atoms present in unit volume of level 2 is n2 of 0. Now as the time increases, you can see from this equation this number n2 in second energy level decreases exponentially, and when this t will tend to infinity, then you can see this n2 t will tend to 0, because when t will be infinity, e to the power minus infinity equal to 0. So the graphical plot of n2 of t in against of this t is like this. This is just almost parallel to the t-axis, which means this will intersect it at infinity. Okay. Now consider a particular value of t. Particular value of t we consider. So if we take t equal to 1 over a21, it means we take a time t reciprocal of this Einstein coefficient a21. Then see that equation. What will be n2 of t? This n2 of t will be equal to n2 of 0 e to the power minus 1, because here there is a21 into t and t is 1 by this much, so this will be minus 1, and this is n2 of 0 divided by e, and this will be equal to 0.37 of n20. Okay, n20. So actually the time which is reciprocal of this Einstein coefficient A is just in that time interval, actually the number of atoms in this second energy level has become only 37% of the number which was present initially there. So this is 0.37 of n20. Okay. Actually, this very time which you have considered equal to a reciprocal of this Einstein coefficient A21, this time is actually called a spontaneous lifetime associated with the transition 2 to 1. So t equal to 1 by A21, and this is equal to TSP, and this is actually called what? This is called a spontaneous lifetime. Associated with transition 2 to 1. Okay. So I hope you have understand these things, and you can define this spontaneous lifetime as the time interval during which the number of atoms per unit volume in the second energy level becomes the 37% of the total number of atoms per unit volume in that level 2 initially. So that duration of time is called a spontaneous lifetime, and it is denoted by the symbol TSP. Actually, we will find the application of this spontaneous lifetime in our further concept on laser.